Welcome to This Explainer. You know, whether you're a geographer studying massive climate shifts or an economist tracking inflation, raw data is, well, it's just chaotic. There's so much of it. So today, we're exploring the mathematical magic of finding the signal in all that noise. And we're going to do that by pinpointing the absolute center of our data.
Okay, let's dive into this, because this is really the core problem we face in any kind of data analysis. Imagine trying to understand the rainfall of an entire region over a year, or the daily wages of hundreds of factory workers. You literally can't process every single data point in your head. It's impossible. We need a reliable way to distill thousands of wildly varying observations into one powerful representative number.
To ground this math in reality, just think about the physical world around us. From varying rainfall levels across different districts to population density shifting from city to city, geographical and economic phenomena vary wildly. They're all over the map. If we want to truly understand these patterns, rather than just, drowning in a sea of numbers, we absolutely need robust analytical tools to process this information efficiently.
Here is our roadmap for today. We'll start with the center of data. Then look at the mean, median, and mode. After that, we'll calculate the mean of ungrouped data, and finally, wrap up with the mean of grouped data.
Section 1. The center of data. Finding the representative figure.
Whenever we're faced with measurable characteristics that vary a lot, we look for a singular anchor. And that anchor is formally called a measure of central tendency. By definition, it's a single value or number that best represents all observations, usually lying right near the center of a distribution, rather than at either extreme. You can actually think of it as the gravitational center of your dataset. It's the exact point about which all your individual items have a natural tendency to cluster.
Section 2. Mean, median, and mode. The three heroes of data.
These three measures, also known as statistical averages, each provide a totally different lens for viewing our data. The mean is your classic, everyday arithmetic average. The median requires ranking your data and finding the exact middle point, kind of like the median strip on a highway. And the mode, well, it just looks for the most frequent, popular value in the whole set. So the crucial point is that each of these measures is perfectly suited to different types of data sets. But for the rest of this explainer, we're going to put the narrative spotlight entirely on the mean.
Section 3. Mean of ungrouped data. The rainfall of the Malwa Plateau.
Okay, we're going to anchor our very first calculation in the real world. Notice the varying normal rainfall in millimeters across these 7 distinct districts in the Malwa Plateau. Mansour is on the drier end at 825 millimeters, while Dewas gets quite a bit more at 1,083 millimeters. Because we have individual, highly specific values for every single district here, this is what statisticians call ungrouped data.
To find the center of this rainfall data, we use the direct method. It's beautifully simple and relies on just 2 straightforward steps. Step 1, we add up the rainfall values of all 7 observations. Easy enough. Step 2, we take that total sum and we divide it by the total number of districts, which we represent in the formula with the letter n. And ta-da! When we add up all those varying rainfall numbers, we get a total sum of 6,484. We divide that by our 7 districts, which gives us our direct mean, 926.29 millimeters. That single number elegantly represents the average rainfall for the entire Malwa Plateau. Simple, right? But hold on. What if you're dealing with hundreds of districts, or numbers in the millions? Adding all of those up directly becomes absolutely exhausting, and let's face it, highly prone to errors. Enter the indirect method. Now, I want you to frame this next formula not as more work or just another equation to memorize, but as a really clever statistical life hack to reduce the size of your numbers before you even start calculating. Here's the logic behind this shortcut. First, you just eyeball the data and guess the center. Seriously, just guess. We call this the assumed mean. Second, you find the deviation by subtracting your assumed mean from every single actual value. This shrinks your giant, clunky numbers down into tiny, manageable ones, an operation officially known as coding. Finally, you calculate the mean using these small, coded numbers, and then just add your assumed mean back in at the very end.
Let's look at our rainfall data again. Since the numbers range from about 800 to 1100, let's select a nice round constant of 800 as our assumed mean. In the new column, we subtract 800 from each district's rainfall. So, indoors 979 becomes just 179. DARS 833 becomes a tiny 33. And this brilliantly illustrates how selecting an assumed mean makes the math so much easier to handle. You're just adding up these way smaller deviation numbers. So when we add those small deviation numbers up, they total 884. Divide that by 7, which gives us 126.29. Finally, we add our assumed mean of 800 back to that result, and what do you know? We get 926.29. Whether you do it the brute force direct way or the clever indirect way, you arrive at the exact same mathematically sound answer. No way, right? But it works perfectly every time.
Section 4. Mean of grouped data. Factory worker wages.
Now, what happens when our data sets are so incredibly huge that individual values lose their specific identity and just get lumped into broad frequency distributions? Well, here's our new real-world anchor. We have 99 factory workers, but we don't know exactly what each individual person makes. Instead, they're grouped into 5 wage rate classes. For example, we know 10 workers make somewhere between 50 and 70 rupees a day, but we don't know if they make exactly 51 or 69. Their individual values have essentially lost their identity.
Let's see how this builds our next formula, the direct method for group data. Because we don't have individual values anymore, we have to create a proxy. Step 1, we find the exact midpoint of each wage bracket, which we'll call X. Step 2, we multiply that midpoint by the number of workers in that bracket, which is its frequency, F. Step 3, we add all those up and divide by the total number of workers.
Let's see it in action. Look at the first row. The midpoint between 50 and 70 is 60. We multiply that midpoint of 60 by the frequency of 10 workers, giving us an FX value of 600. We just repeat this for every single row. When we sum up that entire final column, we get our total proxy value, 10,160.
We take that 10,160 and divide it by our N, the 99 total workers. This gives us our direct mean wage rate of 102.6 rupees per day. That single figure beautifully represents the center of this entire grouped data set.
But, as you can probably guess, once again, multiplying large midpoints by large frequencies can yield huge, ugly numbers. Just like before, there's a shortcut. The indirect method for group data minimizes the magnitude of computation by, you guessed it, using an assumed mean. By choosing an assumed mean near the very middle of our series, we save ourselves from massive, headache-inducing calculations.
Let's assume our mean is 100, taking the midpoint of that middle 90 to 110 group. We find our deviations by comparing the other midpoints to 100. Now, what's really interesting about this slide is what happens when we multiply our frequencies by these tiny deviations in the final column. Look at that. We get negative numbers at the top and positive numbers at the bottom. The numbers are incredibly small, and the negatives and positives naturally cancel each other out, making the final sum an absolute breeze to calculate.
When we add those tiny positive and negative numbers together, sum them up, divide by 99, and add our assumed mean of 100 back in, we get the exact same final answer, 102.6. Our clever little shortcut perfectly matched the direct method, once again, but with a fraction of the computation.
So there we have it. We have successfully conquered the chaos of data. We've learned exactly how to find the singular representative figure, the mean, whether our data is grouped or ungrouped, using both the direct path and the clever indirect shortcut. But I do want to leave you with one final thought. The mean tells us exactly where the center is. But remember all those wildly different rainfall levels and those different wage brackets we looked at? If the mean perfectly summarizes the center, what secrets do the internal variations, what statisticians call the dispersion, still hide from us? Finding the center is really just the beginning of the data story. Thanks so much for watching and keep exploring.